Thank you. Is everyone able to hear me?
Yes.
Perfect. Awesome. So yeah, thanks for the introduction. My name is Jessica, and today I'm going to be talking about the processes that govern the morphodynamics of estuarine beaches in Sydney. So estuaries are ecologically and economically really important coastal landscapes. They provide unique ecosystems of high biodiversity and valuable commercial and recreational resources, and are vital for key environmental services such as nutrient filtering. Many modern cities have been developed around estuaries, such as the Yangtze River Delta in Shanghai, the Thames Estuary in London, or Port Jackson Estuary here in Sydney. In pre-modern times, these environments were necessary for the survival of the nascent civilizations, providing food, water, and natural defenses. In modern times, this dependence has shifted away from survival. However, these estuaries still provide the cities built around them with many benefits. Estuaries are exposed to the greatest levels of urbanization and use of any marine environment, and are highly vulnerable to negative anthropogenic effects, such as climate change or the reclamation methods such as dredging. So the term beaches and estuaries and bays, or BEBs, is used to specify local energy beaches found within harbours, bays, estuaries, lagoons, and other semi-enclosed coastal waters, and encompasses all beaches that are built or maintained within an estuary or a bay. Previous classification attempts and management of BEBs have largely involved models developed for open ocean beaches and are unable to adequately describe BEB morphodynamics. As you can see from the figure on the right, BEB morphology is highly variable and dependent on local geomorphology. So this study aims to develop a greater understanding of the morphodynamic behavior of estuarine beaches, particularly relating to the mechanics of sediment erosion and subsequent recovery after storms. This understanding will aid in the management of estuarine beaches both within Sydney Harbour and internationally, and allow for more accurate modelling of individual estuarine beach response to external forces, such as coastal infrastructure, storm events, and climate change. In order to do this, we came up with 3 research questions. Do storm swells have a significant effect on BEBs? Can we identify any mechanisms driving BEB recovery? And are locally generated wind waves or ocean waves the dominant forcing mechanism for beaches and estuaries and bays? So the study area was 12 study beaches in Woollahra Municipal Council, which is a local government area in the eastern suburbs of Sydney, responsible for the management of 16 kilometres of harbour foreshore, which consists of coastal cliffs, rocky headlands, and estuarine beaches. Moving on to the methods. For the hydrodynamics, local waves were analysed at 2 beaches within the estuary. The first was Camp Cove, and the second was Neilson Park. These instruments were located approximately 1.1 and 2.4 kilometres respectively from the estuary entrance. Hydrodynamic pressure sensors were deployed in July 2020 on pre-existing pylons at approximately 1 metre below mean sea level. These sensors measured both water level and hydrostatic pressure, allowing for the spectral analysis of gravity, infragravity, and locally generated waves. 4 storm events were identified during the study period, 1 in May, 2 in June, and 1 in August. The storm in May had the highest intensity, while the storm on the 27th of July was the least intense. Topographic measurements were obtained from 12 beaches along representative transects totaling 51 beach profiles. Profiles were numbered from the north along shore and were perpendicular to the shoreline starting at the back beach and ending below mean sea level. 6 surveys were completed from February to September 2020. Beach profiles were measured using real-time kinematic global navigation system to record a point every meter. Beach width, linear profile volume, and beach gradient were then calculated and plotted against survey dates to generate a time series for each site that detailed morphological change. Decadal evolution at Rose Bay was determined using 6 aerial images, I've shown 4 here, covering 75 years from 1943 to 2018. Images were georeferenced using permanent fixed features with a minimum of 20 control points per image. Shoreline traces from historical images were then merged into a single feature class, and shoreline displacement was calculated by drawing cross-shore transects using the digital shoreline analysis system in ArcMap 10.4 with a total of 74 transects. Outputs from the DSAS tool were net shoreline movement, which is the distance between the oldest and youngest shoreline, and endpoint rate, which was the rate of change, measured in meters per year. A time series assessment for Rose Bay shoreline was then conducted using the net shoreline movement for each individual photograph and plotting the averages in Excel. Looking at the hydrodynamic results, so Camp Cove and Neilson Park showed similar behaviour in the intensity of wave spectra. Gravity sea swells showed the highest intensity for both sites, with a maximum energy of 6.43 meters squared per hertz at Camp Cove and 4.42 at Neilson Park. Infragravity waves were the next most energetic wave type for both sites, followed by the significantly less energetic wind waves. Though energy density for Camp Cove was primarily higher than Nielsen Park for most of the deployment, particularly at the lower frequencies, Nielsen Park had a greater energy density for higher frequency local waves. For the purposes of today's presentation, looking at the topographic results, I've chosen 3 sites to present results for, as opposed to presenting all 12 because we'd be here for an hour. Camp Cove will represent the beaches near to the estuary mouth, Rose Bay for the central estuary, and Double Bay for the inland beaches. The first site we're looking at is Camp Cove, or B2. Camp Cove has varied profile morphology along shore. The beach is characterized by steep linear profiles at the mid-beach and gentle convex slopes at the headlands, the top and bottom profile. Following the May 24th storm, there was significant accretion seen at the northern profiles, while in contrast, the southern profiles saw significant erosion. The July 14th storm had the opposite effect, with the northern profiles experiencing erosion and the central to southern profiles seeing accretion. The July 27th storm saw general erosion across the beach, after which the August 10th storm reported accretion at the northern profiles and erosion at the southern profiles. Across the 6-month study period, Camp Cove saw an overall minimal loss of only 3% beach width, but a more significant loss of 10% volume and 16% gradient reduction. The second beach we're looking at is Rose Bay in the central estuary. This beach has steep linear profiles that are roughly flattened, with the exception of the central profile, profile 4, which has a gentle linear shape. The northern and southern sections of Rose Bay experienced minimal changes in volume and width despite 4 storm events, with volume and width losses of around 5%. Gradient losses following the May and July storms were mitigated by subsequent recoveries, resulting in negligible gradient change. The central section, however, had the highest variation. During the study period, width and volume at the central profile, profile 5, increased significantly while decreasing at the adjacent profiles, P4 and P6, resulting in an overall width increase of 16% and volume increase of 6%. Gradient, in contrast, decreased at all profiles, particularly profile 5, resulting in a significant gradient loss of 28%. Final beach we're looking at is Double Bay for the inland estuary. Double Bay is the site located furthest from the estuary mouth and is characterized by gentle convex curves that turn to a steep linear slope at the southernmost profile, profile 5. Double Bay experienced minimal change in width across the study duration, with an overall loss of only 3% width. Volume and gradient decreased following the July 27th storm, as you can see here. However, recovery following the August storm resulted in negligible changes of less than 1% overall. Finally, looking at the decadal analysis, section 1 was the only section of Rose Bay to have receded over the past 75 years, receding an average of 15 meters behind the 1943 shoreline with a rate of 0.21 meters per year. The greatest period of recession was between 2011 and 2014. And although from 2014 there has been some progression, with this little tick up here, the general trend for this section is still overwhelmingly recessive. Section 2 has experienced significant accretion over the past 75 years, the greatest in the center of the section and diminishing in both directions. Section 3 recorded 2 periods of accretion from 2002 to 2011 and 2014 to 2018. And despite extensive erosion between 2011 and 2014, has seen an overall shoreline progression of 5.8 meters at 0.08 meters per year. Overall, shoreline displacement for Rose Bay was 6.6 meters at a rate of 0.08 meters per year, with the majority of this occurring in the central section between 2014 and 2018. Since 2011, approximately 150 meters of the northern beach shoreline has disappeared, leaving only the shoreline to maintain leaving only the seawall to maintain shoreline location. The amount of sediment lost at the northern end of Rose Bay is interestingly approximately equal to the sediment gained at the central section. Looking at the discussion of our first point, the influence of storm swells, Hardaway acknowledges that ocean swell is able to penetrate estuaries. However, they state much of this energy is lost as it progresses into the estuary. Spectra from the wave pressure sensors deployed at Camp Cove and Nielsen Park can test this, with high energy swell present at both sites during the July 27th storm. And although this swell wave energy does decrease moving further into the estuary, the loss recorded is far less than what Hardaway suggests. And from this, we propose that ocean swell is capable of penetrating many kilometers into an estuary with only minimal energy loss, and is thus able to impact the morphology of beaches and estuaries and bays, even if they are a significant distance from the estuary mouth. There is also a general consensus that high energy conditions drive morphodynamic behavior of BEBs, and BEB morphology is inherited from past storm events. This is consistent with the results that we found, as all 12 study sites recorded significant changes to morphology after storm events. Overall, 10 of the 12 study sites recorded erosion overall for the 6-month study period, with beaches closest to the estuary mouth found to have greater changes in morphology than those further away. From this, we propose that storm events cause longshore and cross-shore transport at BEBs, altering sediment distributions and beach morphology, with increased impacts found closer to the estuary mouth. The second discussion point, looking at the recovery mechanisms from storms, there's some evidence of lowering recovery, with 6 of the study sites recording accretions following the July 27th storm. However, all but one of these sites still ended the study period with net erosion, most significantly at sites near to the estuary mouth. Jackson 2002 suggests that beaches and estuary bays recovery post-storm is often limited due to a lack of STEL. However, we go further and suggest that BEB sediment recovery may be dependent on these less intensive storms that have enough energy to transport sediment back to the shoreline, but not enough to remove significant amounts. Study sites closer to the estuary mouth showed some gradient recovery. However, none were able to mitigate previous reductions and all recorded a net gradient decrease, while the more sheltered inland beaches recorded significant gradient recovery in August and net gradient increases overall. From these results, we propose that more sheltered BEBs experience increased cross-shore transport outside of storm conditions, allowing for gradient recovery without the need for swell waves. Looking at our third research question discussion point, early research by Jackson in 1995 suggests that local wind waves are the main source of energy for sediment transport. However, wave conditions during storm events showed much greater energy densities for gravity swell and infragravity waves. This increase in wave ocean energy resulted in morphological changes at all study sites, with many sites displaying evidence of cross-shore transport, shoreline rotation, or movement of sand to the back beach, resulting in gradient changes. BEBs more exposed to swell, such as those located near the estuary mouth, recorded significant erosion, while in contrast, those protected experienced reduced impacts. And despite significant gradient changes post-storm, recorded minimal overall change in morphology. During periods of modal conditions, there are fewer instances of the higher energy gravity and infragravity waves, with the implication that morphological changes outside of storm events may be the result of local wind waves. This effect, however, is significantly altered by subsequent storm events, with showing that BEB morphology is still dominated by ocean swell. The implications of this is that ocean swell has a much greater energy than local waves and is the primary source of energy for sediment transport, making ocean swell the dominant forcing mechanism for beaches and estuaries and bays. Looking at the case of Rose Bay, Rose Bay's decadal analysis showed a long-term erosion at the northern section, matched with long-term accretion at the central to southern section. This destabilization is not seen at any other site, which indicates that the cause is not related to storm swells. And short-term analysis showed minimal impact from swell waves, suggesting there's an alternative force driving long-term change. There are many potential explanations, one of which is upgrades to Sydney ferry engines, as well as increased ferry services, which came into effect from 2006, which would be consistent with previous research by Nordstrom in 2012 suggesting that boat wakes may have significant impacts on morphology. However, the impacts of boat wakes were beyond the scope of this thesis. In conclusion, looking at our first research question, do storm swells have a significant effect on BEBs? Yes, storm swell is the primary cause of BEB morphology change, altering sediment distributions and BEB morphodynamics, with greater impacts found closer to the estuary mouth. Storm swell was capable of penetrating deep into estuaries with minimal energy loss, causing longshore and cross-shore transport. Looking at our second question, can we identify any mechanisms driving BEB recovery? Recovery was found to be dependent on lower intensity storms transporting sediment from the nearshore to the shoreline, as well as cross-shore transport, with an increased response seen for sheltered BEBs. And finally, are locally generated wind waves or ocean waves the dominant forcing mechanism for beaches and estuaries and bays? We found that ocean swell waves were determined to be the dominant forcing mechanism for beaches and estuaries and bays, as these waves had the greatest energy and most significant impact on BEB morphologies. The findings of this thesis represent a contribution to the still limited knowledge of BEB morphodynamics and may be applicable to other BEBs in similar environments internationally, as well as aiding in the improved management of BEBs in the Woollahra Council area. Looking at future research, despite the importance of understanding estuarine shorelines, particularly in major cities, research on beaches and estuaries and bays is comparatively small. Further research would include wave analysis at inland BEBs, examining the effect of seasons and tides on beaches, and detailed study of beaches near to boat paths or those that are highly modified, as they appear to have altered morphodynamics. Thank you.